Good morning, good afternoon, and good evening. Welcome to the Crazy Hat Chemist. So here we go today with another awesome video here. So just a quick little summary here. And what is today's video? Today's video is gases worksheet number 3. Make sure you watch my 2 previous videos. That's gases worksheet number 1, gases worksheet number 2, and of course, then you're ready to start gases worksheet number 3. All right, so without further ado, here we go. A little summary of the equations that we're going to be dealing with here today. So this equation that I'm highlighting in blue right here, this is the general or the combined gas law. So we'll write general or combined gas law. That's the general or combined gas law. All right, then next up is the temperature conversion between degrees Celsius and Kelvin. So that's the temperature conversion that is in green. And then in orange, what do we have in orange right over here? We have right in orange right here is Graham's law. Graham's law right here. That's Graham's law. This is the rate of gas A compared to the rate of gas B is equal to the square root of an inverse relationship. That's why B is on top and A is on the bottom over here on the right-hand side. Then what we have is PV equals nRT, Pivnert, and that is the ideal gas law. Like right now, you are watching the ideal chemistry teacher work out these problems, and I made this worksheet just for you. That's right, folks. And this right here is the gas constant. It gets replaced into the ideal gas law, just like there. And then over here, this last section here is pressure units. And these pressure units are the pressure conversions. That is, 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 760 torr, which is equal to 14.1 pounds per square inch. All right. Awesome. All right, what we're going to do here is we are going to plow through with our next problem here. And this is number 1. So here we go. It says a gas in a vessel that occupies 230 milliliters at 1.4 atmospheres. So this milliliters lets me know it's a volume. It's the first volume I'm coming across. And then this atmospheres lets me know it's a pressure. That's pressure 1. And then it says, what's the volume? That will be solving for volume number 2. That's the big giant question mark of the gas if the pressure is changed to 730 millimeters of mercury. So that's going to be pressure number 2. All right, so what we're going to be doing here is this is a comparison of of the same gas at 2 different conditions. It's a comparison of a gas at 2 different conditions. So that's why we're going to be using the general or the combined gas law. So the general or combined gas law. So I'm going to rewrite that right here. That's P1 V1 over T1 is equal to P2 V2 over T2. Now, one thing that you notice on this here is that there's no mention of temperature. That means the temperature is assumed to be held constant. And now this is Boyle's law. And I know that we've come across this multiple times here already before, but we're trying to keep it simple, stupid. And this is Boyle's law when the temperature is being held constant. And this is an inverse relationship. If the pressure goes up, the volume goes down. If the volume goes up, the pressure goes down. All right, so what we're going to do is we're going to plug in these values right into this here. So pressure 1 is what? 1.4 atm. And then the volume 1 is 230 milliliters. Just like that, perfect, equals pressure number 2. Pressure number 2 is 730 millimeters of mercury. Now you notice that atmospheres, right here, atmospheres, I'll just highlight this here for you. Atmospheres and millimeters of mercury are not in the same set of units. So what's critical is that you must do a conversion of units to keep them in the same set of units. So that's what we're going to do here right now. We're going to do this off to the side before we plug it into this equation. I just happened to write atmospheres first because it was the first pressure. So I'm going to convert this millimeters of mercury into atmospheres. So I'm going to do this off to the side. We have 730 millimeters of mercury. And every single pressure conversion is a one-step process here. So hopefully that's not going to be too bad for you. But whatever the units are in the numerator here must be the same units in the denominator of the next term. Right? Perfect. So if these are millimeters of mercury, these will be millimeters of mercury. Excuse me. What are the units of pressure that I want? I want atmospheres. So that's why I'm going to put atmospheres in the top. You should see that the millimeters of mercury will cancel out and I will be left with atmospheres under this circumstance. Now what I need to do is find out what these two numbers are associated with atmospheres and millimeters of mercury, and they are right here in the pink. So I'm going to find the atmospheres. There it is. And what's the number? It's a 1. So I'm going to place a 1 in front of the atmospheres. Where's millimeters of mercury? Where's millimeters of mercury? Right there, millimeters of mercury. What's the number in front of it? 760. 760. Now what I can do is plug this into my calculator. That will be 730 times 1 divided by 760. Okay, and I'm going to get a number in my calculator. And first we need to look at significant figures. This number has two significant figures. All the pressures, when we are converting from one set of units to another set of units, they have an infinite number of significant figures. Just like that. So I'm going to plug this into my calculator. This is the number that I'm going to get, and I'll get 0.9605. Now I need to maintain the number of significant figures that I had, which is 2. So that's 1, 2. I'm rounding with that 0, so it'll be 0.96 ATM. All right, perfect. This is the number, 0.96, and the units, ATM, that will go in my equation right here. So that's 0.96 ATM, and then V2. All right, perfect. You should see that the units of pressure are the same on both sides. When I'm solving for the volume 2, what will I get? Milliliters. Okay, so I'm going to now solve for V2. So I'm going to divide both sides by 0.96 atmospheres here. And divide both sides by 0.96 ATM atmospheres. You should see that the atmospheres cancels out. I'm left with milliliters. This cancels out. And now I'm going to have V2. So I'm going to plug this into my calculator. That's 1.4 times 230 divided by 0.96. So 1.4 times 230 divided by 0.96. And the number that pops out in my calculator is 335.41. There are more numbers there, but I'm just interested in figuring out how many significant figures I have in my numbers here. My original numbers, 1.4 has 2 significant figures. This number 230 without a decimal at the end of that number has 2 significant figures. This number 0.96, leading zeros don't count for significant figures, but they're important for placeholdership. So this has 2 significant figures. So the least number of significant figures I have within all the numbers in this problem is 2. I'm going to round this number 1, 2. I'm looking at that 5 for rounding. So my answer will be, and that's 5 or greater. So I'm going to add 1 to the preceding digit. So I'm going to have a 3, 4, and a 0. There's no decimal here. That will give me 1, 2 significant figures. The units are milliliters. I'm going to circle that because that is my correctly calculated and rounded answer. Oh yeah, awesome. That's perfect. All right, now what we're going to do is we're going to carry on to problem number 2. It says a sample of gas is at the following conditions: 15 milliliters and 0.85 atmospheres. What is the pressure? What is the pressure if the new volume is 28 milliliters? Okay, fantastic. So here I have So this is a milliliter, so this is volume 1. This is an atmospheres, so that's pressure 1. What is the pressure? That's pressure 2. That's our question mark. That's what we're solving for. Milliliters, that's volume 2. So what we're going to do is we're going to be writing down the combined or general gas law. Why is that? Because I have two volumes. I have a volume 1 and a volume 2. I have a pressure 1. I'm solving for pressure 2. So P1 V1 over T1 is equal to P2 V2 over T2. Okay, and then what we do right over here is, well, we're going to do like what we did previously, and that is we're going to cross out the temperature because the temperature is being held constant since it is not mentioned in the problem whatsoever. So P1, what is that? That's 0.85 atmospheres, 0.85 ATM. That's my first pressure. My first volume is 15 milliliters, 15 milliliters. Okay, is equal to, and then my second pressure, that's what I'm solving for, and my second volume is 28 milliliters, 28 milliliters, just like that. All right, we're going to verify that our units are the same for the volumes. They're both in milliliters, and the pressure too will be in atmospheres. I'm going to solve for pressure 2. So I'm going to isolate the pressure 2 all by itself. So I'm going to divide both sides by 28 milliliters. That's 28 milliliters. I'm dividing that by both sides here. That will cross out both of these right here. It will cross out the milliliters, and I will be left with atmospheres. So we're going to plug this into our calculator here. Our P2 is going to equal, as our calculator value, 0.85. So 0.85 in my calculator times 15 divided by 28. And that will get the following number, 0.455357. That's way too many numbers than I need. I'm going to look at the significant figures that I have in this problem. The leading zeros don't count for significant figures. They're important for placeholders. I got 1, 2 significant figures, and then 1, 5, that's 2 significant figures, and then 28, that's 2 significant figures. So the fewest number of significant figures is 2. Leading zeros don't count. That's 1, 2. I'm running with that 5. That's 5 or greater. I'm going to add 1 to the preceding digit. So my answer is 0.46. The units are atmospheres because I am certainly looking for a pressure. Perfect. Remember, those leading zeros don't count, but they're important for placeholders, so that's why I've got that there. That looks fantastic. You guys are doing a fantastic job here, and so let's see if we can continue on. So what we're going to do is we're going to slide this up and keep on going. All right, number 3. Here we go, number 3. Says calculate the temperature. So calculate the temperature, that's T1. If the new conditions, 25 milliliters, that's V1. 1.3 ATM, that's P1. And the original conditions are 55 milliliters, that's V2. 25 degrees Celsius, that's T2. And 20 PSI, that's P2. Okay. Again, what we're doing is we are using the combined or general gas law. So P1 V1 over T1 equals P2 V2 over T2. All right, so what we're going to do is we're going to jam all this stuff into there. So let's see if we can do that. All right. So here we go. P1. What is P1? P1 is 20 PSI. So 20 PSI. That's pounds per square inch. Okay. And V1, that's 25 milliliters. 25 milliliters. T1 is what we're solving for. So we'll call that T1. That's there just like that. And then P2, that's pressure 2. Now it needs to be in pounds per square inch since this one, the first one that we wrote down is in pounds per square inch. No, folks, I think we messed up here, folks. We need to rewrite this. All right, so let's give this a try again. All right, here we go. Let's try this again. Calculate the temperature of the new volume. So we have 1.3 atmospheres. That's actually P1. Hopefully you were catching on with this faster than I was. So that's 1.3 atmospheres. All right, there we go. That is our P1. All right. So hopefully all of you are listening and watching that going, whoa, crazy hat, man. You are crazy. You're messing that one up. And hopefully you were faster than me. All right. Volume one is the 25 mils like I had before. And then, yes, we are solving for T1. All right. Now what we're going to do is we're going to plug in our second pressure number two. That's in PSI. So we need to convert that to atmospheres. So 20 PSI, we're going to convert this into atmospheres. So we're going to look at our top of our worksheet right up here. And we have PSI 14.7 and 1 atmosphere. These two things are equivalent to each other. So let's see what that turns out to be. We have 14.7 PSI is equal to 1 ATM, 1 atmosphere. Just like on the previous pressure conversion with problem number one, this has an infinite number of significant figures. This has an infinite number of significant figures. This has one significant figure right here. So 20 PSI times 1, that's 20, divided by 14.7, and that will be 1.36. I'm going to round that to one significant figure. I'm using that for rounding, so this is going to be 1 atmosphere, 1 ATM. That still has one significant figure. The volume is 55 milliliters for my second volume, and then the temperature is 25 degrees Celsius. So I need to convert this into Kelvin. So let's see if we can slide this on up here, and we're going to be using this equation. So degrees Celsius plus 273 is equal to the Kelvin temperature. So I'm going to plug in 25 degrees Celsius here, add 273, and I'm going to get 298. Perfect. So I'm going to slide this on up here again, cruise on up to our problem. And so this is going to be 298 Kelvin. All right. Fantastic. So now what we're going to do is we are going to solve this problem here mathematically. And so hold on and make sure that you watch this. In order to solve this, we're going to cross multiply. So I'll do a really quick little aside problem. If we have, let's say, the number 2 over x is equal to 3 over 5, what we're going to do is cross multiply. That's 3 times x, and then 2 times 5, and then divide by the 3 on both sides. So we're going to do the same thing here. So that is T1 times the atmospheres and milliliters. And then what we're going to do is this here, right here. This is cross multiplying. So I'm going to write all that out so that you can clearly see that, so you can see what we're doing here. Okay. And so we're going to have 1.3 ATM times 25 milliliters times 298 Kelvin is equal to T1 times 1 ATM times 55 milliliters. Okay, that's what I've done is I've cross multiplied. I am trying to solve for this T1, so I want to isolate this all by itself. Therefore, I'm going to divide both sides by what's next to it. That's 1 ATM and 55 milliliters. All right, so that's divided by 1 ATM and 55 milliliters. Just like that. These cancel out. These cancel out. Just like that. These milliliters cancels out. Okay, and these atmospheres cancels out. I'm left with Kelvin, which is a temperature, and I'm really quite happy with that. I like that. T1 is going to equal 1.3 times 25 times 298 divided by 1 divided by 55. So let's see if we can do that. 1.3 times 25 times 298 divided by 1 divided by 55. And the number that I get is 176. Now I need to round this to the correct number of significant figures. Let's find out what that is. This is 2 significant figures, 2 significant figures, 3 significant figures, 1 significant figure, two significant figure. The fewest number of significant figures is a 1, so I'm going to round this to one significant figure. I'm using that 7 for rounding. That's 5 or greater. I'm going to add 1 to the preceding digit. That will be 200. It has one significant figure. It needs to have units on it, and that's Kelvin, and that looks absolutely fantastically beautiful. Ooh, you guys are doing a fantastic job. So, hey, here's a quick little advertisement from our sponsor. Greatly appreciate our sponsor. Our sponsor for today's video is the Crazy Hat Chemist, and that's me. Booyah, booyah, booyah. All right, so just a little breather right here. Time to grab a glass of water and pause that video, use the restroom real quick, and come back here, and then we can finish this up. We got 3 more problems to do. Let's see if we can do that. Thank you very much for watching this video in its entirety. I greatly appreciate that. And that is from start to finish. Don't just watch the answers and then throw down the answers, because then you are not actually learning. You need to watch every single step, and then you will actually learn the basics of chemistry, and then you'll be able to proceed on and then continue on with your chemistry or just with your critical thinking skills. That's what I'm trying to do, is to help you out with your critical thinking skills. So please watch the video in its entirety. I would greatly appreciate that. And also, if you are enjoying the learning on here, please give me a thumbs up. I would greatly appreciate that. It encourages me to make more videos. And I would also greatly appreciate it if you subscribe to my YouTube channel, and that would greatly help me out. Maybe one of these days I'll actually, yeah, have enough videos and enough hours that you'll note it. All right. So let's continue on. We're going to continue on here. We're going to do number 4. So problem number 4, it says, which gas is faster and by how much? So we got 2 questions within one in comparing carbon trioxide, that's carbon trioxide, and chlorine at the same temperature. At the same temperature is absolutely critical on this, and chlorine is a diatomic, so that's why that is like that. So that's a diatomic. So what we need to do is we need to pull out our periodic table, and we need to get the molar mass for both carbon trioxide and chlorine. So carbon is right here. Oxygen is right here. That's 12.01 for carbon, 16.00 for oxygen. I'm going to multiply that by 3, and then I'm going to get a molar mass for that compound. Okay, so we're going to get the molar mass for carbon trioxide. That's 12.01, and 16 times 3. We're going to add those up, and that will be what number? That will be 60.01 grams per mole for carbon trioxide. For chlorine, notice that chlorine is a diatomic element. There is chlorine right there. We're going to take the molar mass of 35.45. We're going to multiply that by 2, and that will be 70.90 grams per mole. Okay, so now we have the molar masses of both of these formulas. Okay, so which one has the higher molar mass? This number has the higher molar mass. It's slower. Which one has the lower molar mass? This has the lower molar mass. It's faster. So the question is, why is the lower molar mass the faster one? Well, imagine me on a skateboard, and I'm just on a flat, even surface. I'm on a skateboard. You take and you push me as fast as you can. All right. I'm going to go a certain speed. Now, imagine me in my pickup truck. I have it in neutral. I'm in the driver's seat, and you get behind my pickup truck and you push me with the same kinetic energy that you used to push me with the skateboard. Which one am I going faster? The skateboard or the pickup truck? The skateboard, I'm going much faster than the pickup truck. I'm going slower. So at the same temperature, the same kinetic energy is applied to these gases. The one that is lower in mass is faster. The one that is higher in mass is slower. Hopefully that makes sense. Now what we need to do is answer the question of how much faster is this gas? Well, that is all dealing with Graham's law. And so the faster gas is going to go on the top. So rate of faster gas is CO3. Rate of slower gas, Cl2. Then it is the equation, which is the square root of an inverse relationship of their molar masses. And I'll just scroll this right back up over here. We are using Graham's law. This is an inverse relationship. Notice that A is here, A is here. And then B is here and B is here. That's an inverse relationship. So we're using that relationship to plug into this equation here. So chlorine's molar mass is going to go right here. That's 70.90 grams per mole. And then carbon trioxide's molar mass is going to go here. That's 60.01 grams per mole. Okay. Now what we're going to do is we're going to plug this into our calculator. It's 70.90 divided by 60.01. And then you're going to take the square root of that. Because one of the most common mistakes is that students forget to actually take the square root after they divide. Don't forget to take the square root after you divide. So it's 70.90 divided by 60.01, and then we take the square root. And we get the number in our calculator, 1.08695. This number has 4 significant figures. This number has 4 significant figures. So my answer will have 4 significant figures. I'm rounding with that 9. That's 5 or greater. I'm going to add 1 to the preceding digit. So I'm going to write this down here to make sure that this makes sense. Rate of carbon trioxide over the rate of chlorine is equal to 1.087 divided by what? Well, if I were to tell you the answer to the problem is 5, what is the denominator of 5? It's a 1. So what's the denominator of this number? It's a 1. So this right here tells you that carbon trioxide travels at a rate of 1.087 times faster than chlorine, which travels at a rate of 1 at the same temperature. Okay. Notice that anytime that you have an answer to this mathematical relationship, anytime this answer is greater than 1, if that number, is greater than 1, then that means that that gas is faster. If the answer is less than 1, then that gas is slower. All right. Perfect. All right, hopefully that makes sense. That's a great example of Graham's law. Now what we're going to do is we're going to see if we can scroll this on up and we can see if we can do the density of what? We're going to get the density of xenon at standard temperature and pressure. Okay, so what is the density of xenon? Well, we need to know the density equation. So the density equation, density is mass over volume. That's generically. Okay, now specifically for gases, there's a special relationship, which is a reorganization of the ideal gas law. So you're going to take the ideal gas law, reorganize it, and you're going to get a density equation as PM over RT. And if you want to figure out how this relationship is derived, then you can look at my honors chemistry video section in the gas unit in there, and I do go over how to derive this from PV equals nRT, the ideal gas law. It's a rearrangement of that to acquire this density equation. So I don't have a problem memorizing this density equation because I am the crazy hat chemist. However, my first real name is Phil, so that's why the P. My last name is Montbriand, and that's the M, so Phil Montbriand. And what school do I teach at? Rio Americano School. And what is my profession? Teacher. So that's correct. Phil Montbriand, Rio teacher. That's how I remember it. That's how that equation was designed originally. Yeah, just kidding. All right. Without further ado, hey, by the way, just a quick little plug here, plug, and that is I am the Crazy Hat Chemist. Please, if you are learning from these videos. I appreciate a thumbs up on that. I appreciate a subscription. Tell all your friends who are taking chemistry to like and subscribe. Throw some comments down. You have a question about something, I'll be happy to answer those comments. Sometimes the comment questions are going out of control. I spend lots of time on that. I don't mind that. I really appreciate that. All right, so here we go. So P is for pressure, R is for the gas constant, T is for temperature, and M is for the molar mass. So the first thing that we plug into this is the gas constant, which is the R. So I'm going to scroll right back up to the top of this problem here, and I have written down the gas constant for you. The R, the gas constant is 0.0821. The units of it are liters, atmospheres, divided by moles Kelvin. One of the biggest mistakes that students make is that they don't actually put the units associated with this in addition to the number. And that's just one of the grave mistakes that beginning chemistry students do. So you need to make sure that you actually have the number and then you have the units. The units are absolutely critical to this. It really helps you out, guaranteed. If you can't cancel out your units, I guarantee you'll have the wrong answer. Okay, so now that is the gas constant. Now we're going to plug in the temperature in here. The temperature must be in units, just like I was discussing, of Kelvin. So the units of Kelvin must be applied here for the temperature. And so under standard temperature, what is standard temperature? It's really nice and easy. It's right over here. It is this number, 273. It is the conversion between degrees Celsius and Kelvin. So what we're going to do is we're going to plug in that number 273. And you should see that the Kelvin units actually cancels out right there. Then what we have is pressure. And the units of pressure must be atmospheres. ATM, that's atmospheres. Why atmospheres? Otherwise, these atmospheres wouldn't cancel out with those atmospheres, and then you'll get the wrong answer. So what is the standard pressure? Well, that is also right here, and that is 1 atmosphere. By the way, just a quick little caveat. If you were to watch any of my honors or AP chemistry videos, 1 atmosphere is actually not the true standard pressure. This true standard pressure is 100 kilopascals. But for this class, we're trying to keep it simple, stupid. And so we'll use 1 atmosphere. There are some textbooks that use the 1 atmosphere. They are incorrect, but we'll just assume that they are correct for this moment in time. Then M is for the molar mass. So we need to find xenon on our periodic table. And where is xenon? Xenon is a noble gas. So here is xenon. I'll highlight that here for you. And here is xenon, and its molar mass is highlighted as well. That is 131.29. 131.29. That's grams per mole. And that is the molar mass for xenon. So now what we're going to do is look at significant figures. So this 273 Kelvin is the standard temperature. That is actually an infinite number of significant figures. Okay, this atmospheres here is standard pressure. That's also an infinite number of significant figures. And then we're going to call this gas constant an infinite number of significant figures as well. If you were to watch some of my other videos, you'll find out maybe it's not so the case. But for this one, I'm trying to keep it simple, stupid here. So that means that my significant figures are all dictated on this molar mass. That's 1, 2, 3, 4, 5 significant figures. So my answer, I'm going to get it, and I'm going to round it to 5 significant figures. So I'm going to have 1 times 131.29 divided by 0.0821 divided by, did I say that? I'm going to say it again, divided by 273. Okay, so 1 times 131.29 and then divided by 0.0821 divided by 273. And I'm going to get this number here. And wait a second, let's just verify this. Yes, that's correct. My number is 5.8576827. And I'm going to round this to how many significant figures? 5. 1, 2, 3, 4 and 5. That 6 is 5 or greater. I'm going to add 1 to the preceding digit. That 7 becomes an 8. So it's going to be 5.858. And then I need units to this. Those units need to be mass per unit volume. So what is the mass that does not cancel out? Grams. What is the volume that doesn't cancel out? Liters. And you can see that the moles cancels out as well from the gas constant. This is why it's so critical that you write the units for the gas constant. So the units for density is mass per unit volume. In this particular case, it's grams per liter. So grams per liter, and then xenon. So let's write down that formula because that would be much better if we did that number units formula. Oh my gosh, wait a second. 1, 2, 3, 4. That's only 4 significant figures. I actually need 5. I was hoping that someone would catch on that. That's why I do this sometimes, so to trip you up. 1, 2, 3, 4, 5. I'm actually rounding with this 8 here, and that will add 1 to the preceding digit. So that will be 5.857, and then that 6 becomes a 7. So there we go. 5.8577 grams per liter of xenon. That way, for those of you who are just like throwing down numbers and stuff like that, you're not really paying attention. You really actually need to watch the video to figure out what the heck is going on. All right, good. Sometimes us teachers make mistakes because we make mistakes and we're human. And sometimes we make mistakes because we do it on purpose. So to make sure that you're actually paying attention to see if anybody in the class says, hey, yo, crazy hat, dude, are you making a mistake? I actually made a mistake earlier on this worksheet, and that was not on purpose. This one was. All right. Here we go with our next problem, number 6, the final and last problem here. That's all right, folks. So again, make sure that you are liking and subscribing and you know what to do. Okay. If you have 0.0015 moles of argon gas at 2.1 liters, 32 degrees Celsius, what is the pressure in atmospheres? So you don't have 2 volumes, you don't have 2 pressures, you don't have 2 temperatures. So therefore, what equation are we going to use? Oh yeah, the ideal gas law. Like me, I am the ideal chemistry teacher. In person, certainly. Am I the ideal chemistry teacher online? Oh, of course I am. So we're going to write down this equation, PV equals nRT. So we're going to scroll right back up here again. PV equals nRT, and we're going to plug right into that. Okay, so the first thing that we plug into this equation is the gas constant. So I'm going to just write an equal sign right here, and I'm going to leave a space for this N, and then we're going to write the gas constant, that is R, that's 0.0821 liters atmospheres, moles, Kelvin. Okay, again, I tell all my students, what do you plug in first? You always plug in the gas constant first. Okay, then what we're going to do is we're going to plug in the temperature. The temperature needs to have units of Kelvin. Okay, that needs to have units of Kelvin. So my temperature is 32. I'm going to scroll right back up here again. I'm going to plug in 32 into there. I'm going to say 32 plus 273. That's going to be equal to 305 Kelvin. So I'm going to plug in 305 Kelvin into this. 305 Kelvin. Perfectly. That allows us to cancel out these units of Kelvin. Then this next one here, that's my temperature. Then the next one is N, that is moles. So this is moles. Now I need to figure out the number for moles. And that is right here. That is the 0.0015 moles of argon gas. Then moving backwards, I got V for volume. That must be in units of liters. By the way, the moles will cancel out with these moles. Okay, all right, perfecto. And then V for volume, that is going to be 2.1 liters. And then what am I solving for? I'm solving for pressure. So there we go. So hopefully this isn't so bad. So now what we're going to do is we're going to divide both sides by 2.1 liters. So divide this side, 2.1 liter. That will cancel this out, cross that out, and divide this side by 2.1 liters. Okay, you should see that the liters cancels out. Liters cancels out. What is the only set of units that does not cancel out in the ideal gas constant is this right here, and that's atmospheres. So that's what we're looking for. All right, that is looking good there so far. So now what we're going to do is we're going to plug this into our calculator. Pressure is going to equal to 0.0015 times 0.0821 times 305 divided by 2.1. So 0.0015 times 0.0821 times 305 divided by 2.1. And I am going to get the following number, 0.017886. I'm just going to plug that in one more time to make sure I haven't messed up. Yep, we're looking really good. Okay, now we're going to look at significant figures, and this number, leading zeros don't count for significant figures. They're important for placeholders. This has two significant figures. This has an infinite number of significant figures. We'll stick with that for this particular set of videos here. And then we have this has 1, 2, 3. That's a captive zero. Captive zeros count. So that's 3 significant figures. And then this is 2 numbers. That's 2 significant figures, all non-zero integers. Fewest number of significant figures I have is 2. So leading zeros don't count except for placeholders. 1, 2 significant figures. That is the 8 that I'm rounding with. That is 5 or greater. I'm going to add 1 to the preceding digit. That 7 is going to become an 8. So the pressure is going to equal 0.0. Those zeros are important for placeholders. 1, 8. And then the units that did not cancel out, I highlighted that. And that is atmospheres right there like that. And that is our answer. Fantastic. You guys have done a fantastic job. I'm the Crazy Hat Chemist. Please like, subscribe, do all that kind of good stuff. You know, submit some questions, some comments. Tell your friends, your neighbor, tell your pet cat, tell your pet dog to like and subscribe as well. I greatly appreciate that. And for all the views, for all of those who have actually watched this video in its entirety, I greatly appreciate your attention. This is the place where you are to learn real chemistry before the world collapses so that you can actually have a good job. All right. I'll see you next time. Bye for now.